Mr. Davidson.
Yeah.
Give me a second book for this class.
No, just the one book.
Okay, because I remember email from book bundles saying I need to pick up another.
That is really odd. I'm not too sure why they would be saying that. Yeah, you just need the original textbook, the Stewart text, and you're all set. They probably made a mistake on somehow with that book bundle thing. Weird. Let me know how that goes. And if they're requiring a bunch of books, that'd be completely weird. Anyone else have a weird experience with the ISU book bundle? They gave you two books? Weird. Yeah, they should have only been giving one. I think what's happening is the old bookstore like to give people different ways to get their book. A hard copy, a used copy, an online copy, a loose leaf copy. And I think they just took all those options and decided you needed that. Weird.
Yeah, because this one's a.
That might have been what they did. Yeah, they're only supposed to be giving you one version. They're screwing up somehow. I think they're not charging you extra though, right? It's still the same rate. Maybe ISU just is gonna be kind of in the red after this. Who knows what's gonna
I can
happen?
say confidently they were trying to give me the online book as well.
Weird. Yeah. I'm not too sure what I would do with them. I guess if I was feeling charitable, I'd probably give back the version I didn't want or something like that. But I'm gonna make a note of this and see if I can say something to the chair and see if there's something they can fix. So book bundle is giving an online version, a loose leaf, and a hard copy. I mean, that's nice to be prepared, kind of generous of them, but that's probably not the intention. I'll send this up to the department chair and see if he knows anything about this. I don't think you're going to be charged extra because it's just rate per credit, but someone's making mistakes somewhere. We've got to find that out. So thanks for letting me know about that, folks. Well, other questions or comments so far, folks, at the moment? Okay, and full disclosure, another thing that's weird is, I think we mentioned this before, but now that we're talking about the book bundle, let's talk about it some more. The upper level administration emailed all instructors and said, add this tool to your Moodle page. Everyone was supposed to call it course materials, but that might vary on your experience. And I've heard from students that when they click on that, it doesn't work in any of their classes. It doesn't work in this class. It just says something along the lines of you have no course materials. It's really kind of weird. So there's obviously some things they need to figure out about that. But the hope is that you're not being charged any extra. Maybe ICU is losing money on sending out all those different versions.
I think the course material is for you can have a book on my county class is an online book, and so another class I have, and I have Google talking about the.
That makes sense. I have a stats class that does homework online, my stats lab, and that's the one class it works in. So maybe that's the thing I didn't clarify. Only put this on there if you have an online class or online homework. Yeah, go ahead.
Set B aside.
24.75 per class credit.
Okay.
Yeah. Sorry, say again. Gotcha. You might have been charged again then, as I understand, because yeah, let me see if I can find that. This is good information because it's so confusing. Let me go to isu.edu. I think if you click on a search along the lines of book bundle, something's going to come up. Here it is, ISU book bundle. And this right here, they sent everyone an email, I guess, but you have to question the ethics of opting everyone in by default, like you're saying. Yeah. Click on that and they say the opt-out period is through September 6th. Yep. Yeah, I would get that done before the due date. Otherwise, yeah, you might already have the book and get charged additionally. That's just kind of crazy. The better end is to pay it once and get like 3 different versions of the book. That's a nicer mistake on ISU's part, at least. But other questions about any of that so far, folks? Definitely being a big question mark this semester, getting it figured out. We'll see if they continue with this idea. Well, we're now on the section 7.2 notes, and that means we completed, let me put this just for a moment again. 7.1 notes, the assignment is going to be due the 29th of this week. I'm taking late work, but again, to be considered caught up, which is really the fundamental way to get through a class like this one, is staying ahead and staying caught up rather. Try to get these done by the due date. I would, for my own personal grading, I wait till the due date goes by, then I just grade the full set of papers. And again, if you turn in a hard copy, I'll be returning you a hard copy. If you email me a digital copy by either of these methods, then I'll just be emailing you back your homework. So the next section is 7.2, so we have our next assignment. And these assignments, I'm going for about 10 problems, feels like a good length for each one of them. But occasionally you might see that there's a reduced set. That just means there's probably longer problems on that set there, and that keeps it about the same length. So my goal is to kind of make each one of the homework sets about the same in length. So this just is indicating probably longer problems on that one is what we'll find. Well, other things to mention is we're going to be getting into some of these trig identities. These are contained in the notes as well, so I'll highlight when they come up. I did give some hints on these two exercises for the 7.2 homework. A trigonometric identity is useful at the very first step to get started on those. If you're not sure how to get going on them, just send me an email, send someone in class an email, study group. I'm happy to personally help you out on those. Well, any last questions at all, folks, before we jump into 7.2? Okay, well, let's get started. Well, we did start in last week on Wednesday's class, and this is where we left off on part B of example 2. Scrolling up to where we began, this is the entire strategy that our author provides for getting through a trigonometric integral. But really the big idea is this is simply a u substitution. And if you forgot all this stuff here, really the strategy is try one u substitution. If sine doesn't work, try a different one, cosine, and you're in really great shape. But it's nice to have guidance when you have it. So when you're studying this stuff, we'll read this up and go along with it. Trying hard to find a good screenshot. Let's go right about there. So we'll see how that information plays a role into these problems as we go to solve them. Starting with this one right here. So we have sine power 5, cosine power 6. Sometimes multiple u substitutions could work. There's more than one way to answer these questions occasionally. But the overall guidance is looking for something that is odd. If the sine of power is odd, or excuse me, if cosine has odd power, that's a good substitution. Already this doesn't look good. I mean, why not? Let's actually run through it and see what goes wrong with this. I'm going to delete this in a moment. It's good to just try something out when it comes to u substitution. So even if you forgot all of this, knowing when a u substitution works is even more important. So if we went u equals sine x, what goes wrong? D would be cosine x, dx. That means here we would lose one power of cosine. We would have to give it up to the cosine x dx to form du. We'd be left with cosine to the power of 5x. And it's because of that power being odd, this is not easy to write in terms of a sine function and still integrate. So that's the only thing that went wrong. So we just are going to backtrack a little bit and try a different u substitution. So it looks like the notes really are trying to get us the right thing. We notice the power on sine is odd, so it suggests cosine should have been the right substitution to make this go through. Let's put it to the test. If u is cosine x, let's use a color on that one, then du is going to be equal to negative sine x dx. How does this one help us? Well, we have to give up one power sine inside here. That leaves us with an odd power sine, and we can correct that. When we do a u substitution, anything that's going to be even powered left over should work out. But let's double check. Let's go here and write this in as we want the integral of observing sine has to go away. I'm going to partition this as sine power 4 of negative 3x. Oh, I did make a mistake there. This was almost ready to go, but looking at the problem a little bit closer, u equals cosine x would have worked. But what should we really use up here in our problem? Exactly. Sorry about that. Looked like a good one to start off, but in our problem, we don't have x's at all. The input is negative 3t. Let me strike that one through. Let's let that mistake stand, since that's a mistake you definitely don't want to make. And let's try again. U equals cosine negative 3t. A little bit more annoying, but now we're doing the right problem. That means du is going to be negative sine of negative 3t. Now we use the chain rule and differentiate the negative 3t. Produces another negative 3. I'll write it this way to indicate multiplication dt. So that's what we're really dealing with in this problem. We have altogether a positive 3, so this is 1/3 du equals sine negative 3t dt. There's other interesting things you could do with these negative signs if you work with the odd and even function properties of sine and cosine, but it's okay to just keep it direct like this if you prefer. Makes it a little bit simpler. We're not trying to do multiple things at once. So now looking again at du, we give away one factor of sine negative 3t. So coming back here, we should write this as sine power 4. Yeah, go ahead first. Oh, the negative sign right here canceled with that negative sign. So we were dividing a positive 3. But thanks for watching out for those, because I am a victim of losing a negative sign. So let me know at any time that might happen. So next, let's call this sine power 4 of negative 3t. Cosine power 6 of negative 3t. That one's going to be easy to handle because that's now just u power 6. Left over is times sine negative 3t dt. And let me put a little border here just so that these don't get too mixed up. So that's our integral so far. Let's look at how we're doing. Fix that border first. This portion right here is going to be equal to 1/3 du. So no trouble at all in this section. Over here, that's just going to be u power 6. All we have to deal with is this right here. So we'll use some trigonometric identities, like these ones indicated down below, to help us out. This one's for sine power 2, but you can just square that whole equation by the red dot, and now you're dealing with sine power 4. So this is how we typically write this out.
I'm sorry, I got a quick question.
Yeah, go ahead.
I might have missed it. When did the sign become to the power of 4 when you wrote it down right there?
Oh, what happened there was, when I saw this sign right, oh, didn't mean to scribble on it, Control Z that. When I saw this sign negative 3t right here, had to come out for the du equation, I took sine power 5 and broke it into two factors like that.
Okay, yep, that makes sense.
So really all I'm doing is just kind of splitting things off and organizing to see what extra algebra has to occur. This bit right there. Other questions at the moment? Okay, thanks for asking about that. This is what makes these integrals a little bit wild in a certain sense. You might notice that the most steps I take here on the left column is mostly organizational before we even begin to integrate. So next thing to work on is that right there, sine power 4 negative 3t. Let's write it out so we're not writing down an integral equation, a bunch of extra steps. That's a lot of writing on your hand. We'll just separate it out in the margin. Sine power 4 negative 3t equals essentially this equation here with a negative 3t baked in, all squared. So 1 minus cosine squared negative 3t to the power of 2. So what I did was took this equation, squared both sides. So now I have a power 2 there, excuse me, a power 4 there, and a power 2 here. Does that make sense to folks on that approach? Okay, next is just ordinary algebra. We need to crank out, FOIL the 1 minus cosine squared negative 3t on the right-hand side. So first it'll be 1 times 1 for a 1 squared. 1 times cosine squared negative 3t comes in twice. So minus 2 cosine squared negative 3t. And then finally cosine squared negative 3t multiplies itself plus cosine power 4 negative 3t. So that's a result of squaring out this right here. So all that goes in this position. And here's our next step. Give it a lot extra space. We're integrating. Let me highlight in yellow this portion right here. I'm running out of colors, but I think this is a good correspondence. That is turning into that right there. We're just going to write it in. 1 minus 2 cosine squared negative 3t plus cosine to the 4th power negative 3t. I don't like that exponent. I think we can make it bigger. Okay, so that's a 2 there. The rest is just copying in cosine power 6 negative 3t. And I really didn't take into account how big this problem could get. So let me just try to squeeze in more space. Last times sine negative 3t dt. Oh man, it almost fit. Let me see if I can get that in one last try. Sine negative 3t dt. And my border is getting a little bit unstable, but we'll work with that. I think that's as wide as this problem gets. That look right to folks so far? Okay, so now we're going to bring in our substitutions. We have a substitution here, here, here. That's all going to be different powers of u. This right here is going to turn into 1/3 du. That's our sine negative 3t dt. So we're basically home free. The integral starts bad. It gets different levels of worse, but the end progress or the end goal in all of these notes is to bring it back to the level of calculus 1 type integral. It now looks like this. 1 minus 2 u squared plus u power 4 multiplying u power 6. Then we have in there 1/3 du. Normally I put that 1/3 right on the front, but I just forgot it was there. So if you have it included, you're in good shape. So we're on our way, folks. If you're doing this in a calculus 1 class, you probably would take that step, move the 1/3 outside of the integral as a constant rule. You definitely don't want to integrate two polynomials being multiplied or divided. So now you want to distribute u power 6 inside. We've got u power 6 minus 2 u power 8 plus u to the 10th power du. And suddenly the problem becomes relaxing at this point. We're just going to use the power rule in reverse 3 different times, undo the substitution, and we're on our way. Now, I'm going to leave this taken out just so that notes become more readable. That's starting to look like a distraction to me as well. Well, any questions at all, folks, to this stage? Okay, this is basically the experience on every one of these problems. Get it down to something like that with the right substitution. Sometimes more than one substitution can work. So if your answer is different from the odd answers, don't fret too much. You could send me an email and say, hey, Mike, are our answers equivalent? I got something different, and I'm happy to check it out. So proceeding further, we get an antiderivative here. I'm going to call this 1/7 u power 7. You can save a big step right here if you want to write a little bit less. We already know that u is cosine, so if you put cosine to the power of 7, negative 3t, that's a good step to skip. I'll write this in just so the notes are a little bit more readable. Next, it's minus 2/9 u power 9 plus an 11 u power 11 plus a constant. And I'm thinking when you see something like this, you always want to make a judgment call. You could distribute the 1/3 inside, but I'm thinking I would just leave it factored out. There's no cancellation doing that distribution, so it's just extraneous work for no apparent benefit. I'd leave it in as 1/3. 1/7. Now it's going to be cosine power 7, negative 3t, minus 2/9 of cosine power 9, negative 3t, and I might run out of space on this one again. Oh, geez. If this happens to you, this is an acceptable strategy. You can go like this. Plus 1/11 cosine negative 3t, cosine to the power of 11, negative 3t, close the parenthesis and add a constant. Let me know how this looks. Does this look readable to folks, especially with that parenthesis? Okay, I'll try not to go up to the edge right here as often. I think I just get surprised sometimes how long these questions can get, especially on the horizontal space. I should have just went down a line. But we did it, folks. That's the antiderivative of this right here. It's various powers of cosine is our end result. Any questions at all, folks, on getting to that stage? Okay, so again, that's pretty much the experience of these. They're not all this long. The problem we did above was pretty short. And I mentioned before, in your homework, sometimes you get a really hard problem on like problem 7, and then problem 11 is easy. It's really kind of weird how the problems are written in our textbook. So here's our next one. And, you know, comparing to this integral, it does look way easier, right? In fact, it's slightly trickier, but it really is an easier integral to get through. We just have to navigate the trickiness. So what's our strategy? Our strategy this whole time is to look for an odd power of cosine or look for an odd power of sine. So this problem answers the question of what do you do if there's neither? There is no odd cosine or odd power. Both of these substitutions actually fail each one you try. That's because if u is sine x, du is going to involve cosine, leaving one power of cosine behind. Writing that cosine in terms of sine is not easy, and once you do it, now the integral is way harder. So here's where the half angle identities come into play. If you find even powers of both sine and cosine, you probably want these identities in your problem. These could do the job for us, and in our problem, looks like we need to use both. Here's how I would start off this one. I'm going to work on the margin to begin and just return to the integral. So let's start by saying we've got a sine squared x multiplied by cosine squared x. These identities are things you'd see in a trig class, referred to sometimes as the reduction formulas, depending on the book you studied out of them. But I think they are cool identities because in a trig setting, you don't do much with them except say they're there, here's how they work. Here we get to show the reason why we care about them. It's to enable us to find an antiderivative to something like that, where u substitution fails. We need to drop the powers down. So first for sine, use that formula. 1/2, 1 minus cosine 2x. For cosine, we use this formula, times 1/2. 1 plus cosine 2x. So there they are. Let's consolidate the constants, 1/4. I'll write this in one more time, just so we know what we're multiplying. 1 minus cosine 2x. 1 plus cosine 2x. And now let's expand out these two things by FOILing. So we'll have altogether a 1/4, which multiplies first 1 times 1. Then here to here is positive cosine 2x, negative cosine 2x. So we have cancellations on the middle terms. Last thing to multiply is going this way. And so that's going to be minus cosine squared of 2x. So reducing this sine squared cosine squared takes us down to that step. That looks easier to integrate, but there's still a problem. Integrating cosine squared is actually hard. So we use this formula yet again to drop down the power. So as soon as we have a high power that's even, we need to drop it down. So it goes like this on the next step. Equals 1/4 multiplying. Oh, actually, geez, I'm not sure what steps to take next. I was thinking distribute first, but let's keep on going this route. 1 minus, we use identity here, so that's another 1/2 multiplying 1 plus cosine. And this problem is really all about the patterns. That's some crazy parentheses in there. But what would you say goes in here by the pattern? Good call. In the pattern, what happens each and every time is you take x and you double it as the input. So if the input's 2x, down here is 4x. But now this is kind of a mess and we have to integrate it. So we're going to do some expansions. First, let's distribute 1/4 through. 1/4 minus 1/8, 1 plus cosine 4x. It's a little bit more readable. Now, it's still not nice for integration. Let's distribute the 1/8 through. This is one of those problems that just keeps on going and going, and we haven't even gotten to the integral yet. But here's our next step. 1/4 minus 1/8 minus 1/8 cosine 4x. So this is really 2/8 minus 1/8. This is what we want to integrate. 1/8 minus 1/8 cosine 4x. So that's pretty much just an adventure in trigonometry. Probably a bit of review, but these are pretty common formulas. We'll see them a lot in the homework set. But any questions to get to this stage so far? Okay, now we bring it all together. You could factor out 1/8 and just put it out in front. I'll just leave it all as it is in this one problem. So this becomes the integral of, by the substitution, 1/8 minus 1/8 cosine 4x.
Why is it 1/8? Why happened to the 1/4 and negative?
Oh, right here, I did a quick fraction computation where I really should have wrote this 2/4 as, or excuse me, 1/4 as 2/8. So I got the least common denominator of this one and just brought them together. Thanks for mentioning that. It kind of doesn't really flow in the notes too well. Does that make sense with that correction there?
Yeah.
Awesome. Other questions so far? Okay, so it's a really wonky problem. Most of the work is the algebra right here. Now, when we go to integrate, not so bad. This turns into 1/8 of x. Now, if we find the antiderivative of cosine, it'll maintain this sign, so minus, there'll be a sign 4x, but we're avoiding the u substitution. We're just gonna have to put in the right constant here, so we don't have to do that extra step. Anyone spot the denominator? Good call. We take the 4, divide it into what was already there, and this should be a 32. Add in a constant, and let's double check this part right here. If you differentiated this portion, negative 132 stays where it is, constant multiple rule. Sine turns into a cosine without changing the sign, but then you multiply by the derivative of 4x through the chain rule. That's just a 4 that goes here, and sure enough, 4 over 32 becomes the 1/8. So that is the quick eyeball check of that one. There was no u substitution, so nothing to undo here. All we did is substitute algebra from the original algebraic form. So weird problem, especially when you see the last one. Any questions at all about part C? On the startup right here, that's a good thought, but there comes in some challenges if we go that route. Let's take a look at that one a little bit closer because it's honestly a pretty weird question. Sine squared cosine squared. Dx. We could convey one or the other, right, into purely sines or purely cosines. So for example, sine squared x, by our little handy dandy identity there, could be rewritten as 1 minus cosine squared x. There's still a cosine squared x here, dx. So with this integral, the challenge would be is, even if you distribute through and split integrals, you're still faced with this integral, cosine squared x, and you're also going to be faced with the integral involving cosine power 4x dx. So it takes us to the same difficulty. Integral of cosine squared on its own, that's actually a pretty tough integral to come up with, unless you did this. This is what makes that integral simplified. For this one right here, you could use this formula twice. You just have to square the right-hand side. So that approach would work this way, but it looks like we're still coming down to those same kind of identities if we went that route. We try to, that's a good thought as well. There's two versions we could try. Let's say u equals cosine x. The differential would go du equals negative sine x dx. And now the trouble is, If you split off sine squared, you still have one sine x left over in the integral. You'd have to write that sine in terms of a cosine, and now your interval has square roots. It becomes complicated at that point. Same trouble if you go u equals sine x. On a u equals sine x, du is cosine x, dx, and now you have to split off this one to give it away to the du differential portion, leaving one factor of cosine. If it was just like, say, a cosine cube though, notice that's the best case ever, right? Because then this works. You're left with cosine squared, which you can do that to, or rather that one down there, and now you're in great shape. So the fact that they're both even is what's causing essentially all the difficulty, making these really hard to progress through. But those are great thoughts always. What goes wrong with these two? And on an exam, pretty much that's what it is. If you find something odd, that means one or the other are going to work. Even if you forget the formula, just try one or the other. You'll find the right one really fast. Other questions so far on this one? Or on the post-analysis? Okay, let's try again then.
How
Oh, there was. Oh, sorry, go ahead. And Zoom.
do you know?
Sorry, you're cutting out just a little bit, Jose. I gave you just the first part of your question.
I said, how do you know?
Sorry, couldn't quite hear you. It seems like it's just an issue with your microphone. You could try the chat if you'd like. That might be a little bit better. But I'm not hearing you at all through the microphone. It's broken up right when you start trying to talk. Other questions so far, folks? Okay. Oh, there's the chat. Thanks, Jose. How do you know when to move from the right to the left side of the page? How do you mean with left or right side of the page? Are you meaning, say, the organization, like this kind of stuff? Oh, right here? I would say the reason I stopped right at this level was here, the power is less than 2. And that's what we're trying to get to when we did all this work. So when we had those even powers, we only stopped until we got to that part. The power here was a 1. So that was our stopping point on that one. Does that make sense for that question there, Jose? Awesome. Sorry for the miscommunication there. I think I understood after your second statement there. If you like, you could try jumping into the office hours sometime during the week, and we can figure out what's going on with the microphone and try to get it working for you. But if chat's what works, I'm always happy with that as well. Other questions at the moment, folks, on this one or others? Okay, well, let's try out the next adventure on this kind of stuff. That's this one right here. And when you look at this problem really carefully, you start to realize, well, this advice just doesn't always work. This is for evaluating sine to a power and cosine to a power, yet we have cotangent. There's a fix on that. If you have a cotangent, you could just try expressing everything in terms of sines and cosines, do some simplifications, and potentially this could come back onto the table for us. So let's try to get this all back to the strategy if possible, by just beginning with the integrand. Cotangent cubed cosine squared x. Let's re-express that as something. Again, this is a pretty good review in trigonometry on its own. So if a lot of these ideas feel just a little bit too foggy or vague, on the Moodle website, you can take a look at these notes here for a refresher. And the trigonometry appendix of your textbook is excellent. So take a look at that one as well. So let's begin with cotangent cubed x, that's a power 3, multiplying cosine squared x. First thing I want to correct is the cotangent, expressing it in sines and cosines. What would y'all say is in the numerator for a cotangent? Is it cosine or sine? Absolutely, good call. So that's a cosine cubed. X divided by sine cubed x. All of which is multiplied by cosine squared x. So we're dealing with a cosine power of 5x divided by sine cubed x. Well, it still doesn't fit into this, right? This involves sine in the numerator, cosine in the numerator, but still, it's a good old U substitution, so it's somewhat related. Let's come back over here and write this in as integral of cosine power 5x over sine cubed x, and go from there. Now, if you have numerator and denominator, our choice of U substitution is actually very restricted. For example, I can't pick U to be cosine any longer. The reason for that is if U is cosine, the differential involves a sine function, but my sine functions are in the denominator, not in the numerator. I would have to multiply by sine over sine to make that work out for us, to get sine back up above. We really just are kind of forced to pick the denominator on this one and see if it works out. Let U equal sine x. Then it's differential. Du would be cosine x dx. And the only reason that one works is because cosine is already in the numerator. We can work with that. So what happens next to this integral? It becomes integrate. I need to get above a power of cosine, so I'm going to write this in as cosine power 4x sine cubed x. It's going to multiply the cosine we took out, dx. So we're in good shape on this one. That's our du, right there highlighted in blue. Sine cubed, that's just going to be our u, so we know what this is. We just have to work out the cosine power 4x. So that was not so bad. We've kind of looked at what that strategy should be in related problems. We take that identity for cosine squared, square both sides. So cosine power 4x is 1 minus sine squared x to the power of 2. So we'll pick up on this one and substitute it in, throwing it back into the integrand. Well, any questions, folks, with the approach at the moment? Okay, lots and lots of trigonometry. Honestly, this really feels like a good review of the trigonometric class just on its own. Over here, now it's just algebra. Expanding this would give us 1 minus 2 sine squared x plus sine to the power 4x. Because our u is sine x, we can substitute each one of those quantities. Oh dear, let me fix that. So one more step on re-expressing the integral, and now equals 1 minus 2 sine squared x sine power 4 of x divided by sine cubed x multiplying cosine x dx. We have a substitution here, 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 and here. First of all, these are all u's in the fraction, and this portion is du. So that's our approach. The moment everything that involved x gets substituted out, we know we're on the right track on u substitution. So it's now 1 minus 2u squared plus u power 4 divided by u power 3 multiplied by cosine x dx. Looking that up, that just turns into the du we see right here. Now that we have an integral just in terms of u, this becomes a calculus 1 integral. It's still tricky. We still have to divide u cubed through to make this easier than it is as it stands, but we're well on our way at this stage. Any questions or comments or concerns so far to this step? Okay, the go-to step in this situation is definitely don't integrate the numerator, the denominator. We'll get the wrong answer. We need to divide through to get the integral of u cubed divides here. That's a 1 over u cubed, but I'd rather write that as u power -3, just easier to integrate. Next one is going to be -2 u squared divided by u cubed, I would write this one in a very particular way, -2 times 1 over u. So the 1 over u is important because this reminds us the antiderivative is the natural logarithm with absolute value put in. Then finally, u cubed divided into u power 4 is plus u du. I think I'll go down and not run out of space. I think that's a good next step to take here. So now when we find antiderivatives, we're home free. This goes up by 1, so it's -1/2 u to the power of -2. This one is a logarithm, -2 natural log absolute value of u. Here we get a half u squared plus the constant. And we're not done at this stage, but we're definitely well on our way. We just write everything in terms of sine x. And this is a pretty common shortcut. If you're getting tired of writing these out in your homework, if you put in sine right at this step, that would be an okay shorthand to take. But let me see if I can get it going to the right. I'm running out of vertical space. -1/2. And I want to be really careful with this one. You could write this sine with the power -2 here, but the way you write that has to be conveyed. You have to know that we're not talking about an inverse function. I think the way to be most clear is either write this in as a cosecant or just write the power on the outside. Sine x to power -2. I'd personally probably leave it in that format, but you could turn this into a cosecant squared if you wanted to. Let's write that in. Sine x, power -2. If you prefer, it becomes 1 over sine x squared. But if you're using trig functions, that's just as good as cosecant squared of x. I think that's the nicest way to write it. Albeit like leave it here in this format just to convey you're okay leaving your function in that, like that. So next one, -2. Natural log absolute value sine x plus 1/2 sine squared x. Just about enough space and our constant. After that, let's double check we've got everything in. Looks like we've got it, folks. That's our antiderivative to that mess right up there. Any questions at all, folks, for getting to this step? Okay, I would say the major trickiness about this problem is it's a bit of a surprise to dig back into trigonometry, take something like this, and simplify it. So that's something that comes up a lot in this section. It comes up in the homework as well as section 7.3. So again, lots of trigonometry is coming back. You can save time just by spending a good hour refreshing this in the appendix or elsewhere before diving into the homework if you feel a little rusty. Well, that's all the strategies for evaluating sines and cosines to various powers multiplied. We have one more topic in this section notes before we go to the next page or the next section, and that's tangents with secants. This one is a little bit more finicky. In this one, you might find that there is very often two strategies that work. Sometimes u equals tangent is a right substitution, sometimes secant is, and sometimes both of them work. So this is a good section where your answers, when you compare them to the back of the book, they might look totally different despite the fact your answer is algebraically absolutely correct. So definitely don't second guess yourself too much if your answers look different. Look into if they are algebraically equivalent. So what's the strategy on this one? Well, it says if the power of secant is even, so with secants, you're looking for even powers, you want to use tangent here. Why is that? That's because the differential of tangent would be equal to secant squared x dx. The power over here is even, then pulling off at even power allows you to use further identities, like say this one here, or this one here. So sometimes we use the secant identity, sometimes we use the tangent identity, but it's only if that power was even on that secant. Next one is if the power of tangent is odd, so now we're going back to odds, use that one, equals secant x. Reason that works, well, if the power of tangent is odd, we give up one power. We're back to even powers of tangent where that identity works. And here the differential is secant x, tangent x dx. So if the power started odd, it goes back to even because you give up a tangent. And if it's even, that identity can now be used to make everything in secant. So those are the overall strategies. But once again, nothing wrong with completely ignoring this and just deciding try one or the other and use whatever sticks. That's a valid approach as well. It's honestly just as fast. We'll do it the same way as before. We're going to use this strategy just to see what it's all about, and I'll let you decide your best way to approach these kinds of problems. So what do we have to start? We have an even secant, so strategy A will work. We have an odd tangent, so strategy B will work. They're both on the table. At this stage, we're just looking to solve the problem as fast as possible then. So what tangent or what U would you use in this case? Any volunteers for a choice of U? I mean, they both work. I like tangent. The reason I would probably pick tangent as well is it's just the highest power. So to me, it seems like it might be the least amount of work. I think actually they're both just about the same. So if someone wants to go a different route, I'd say go for it. Let's let that be a U equals tangent. Next up, we need a differential. Derivative of tangent is a secant squared. And that works because that leaves an even power secant behind. That's our main objective. It's good to think those little thoughts as you go. Always second guess this and decide, is it working? Am I getting what I want out of this integral? But here's your differential, secant squared x dx. Now here's the part of the problem where it gets kind of long before it gets a little bit nicer. A lot of mathematics is just organization, so you can visualize what your next step should be. And this kind of organization does reveal the next step. If you saw secant squared here, partition the power of secant power 4. Write it as secant squared x. Tangent's fine just the way it is as power 5. And here's the remaining power of 2 for secant, along with dx. So now that we see that, we realize, well, that's just du right here. Tangent power 5 is just u power 5. If we can correct this portion, we're home free. That's an automatically supplied identity. The base identity really goes like this. Tangent squared x plus 1 equals secant squared x. And this one identity just gets rearranged in various different ways. Here, our author liked to put 1 in front, but you can just solve it and get to this one, solving for tangent squared. Here we're going to be using that identity. So secant squared x is going to be equal to 1 plus tangent squared x, or tangent squared x plus 1 if you prefer. So we're throwing that in. So next step, we have 1 plus tangent squared x, tangent power 5x, secant squared x, dx. Let's take another look at this. That's your du. That's u power 5. That's u power 2. The only thing left over is a constant. So we're well on our way. We just need to do the substitution, crank it out. This, to me, if this was a 5-point problem, I'd probably consider this 3 points out of the 5 because that's the main thrust, just to get to this organization. The rest of it is almost a review of Calculus 1 at this stage. Any questions at all, folks, to this step? Okay, let's make the u substitution happen then. This is now integrate 1 plus u squared going here. It multiplies u power 5. And then last, secant squared x dx is our du. No extra constants or anything like that. This one looks like kind of a fast one to finish off. It just takes work to get to this stage. So first distribute this out so we can integrate cleanly. U power 5 plus u power 7 du. I think this is our nicest integral of the day once we get to this step. This now turns into 1/6 u power 6 plus a 7 u power 7 plus a constant. Finally, we just undo the substitution.
UA.
Oh, good call. I'm not sure what I did there. That was just a mistake. Probably could have lost a point on that one in a real exam question. U power 8 multiplied by an 8. Thanks for spotting that one. As soon as I find that someone spots a mistake, I get suspicious about the rest. Rest look all right to folks so far?
Yeah.
Awesome. Thanks for that correction there. So now we get all together 1/6 tangent power 6 of x plus now the 1/8 tangent power 8 of x and a constant. So this one's done by that substitution. If you use the other substitution and it does work, you get an answer. They look different, but they're only going to differ by a constant. So that's the good news. The bad news is the back of the book only shows one answer. So again, if you're not sure about yours, if it looks kind of weird, you're welcome to just take a screenshot, send it to me, and I'll let you know. So that's our first run at that. Let's try this again next with that thing. But now this time it's a definite integral, so we have to maneuver through that. But really the worst part of this one is, well, the power on tangent is even. Doesn't work with this strategy here. We are on this strategy. The worst thing you ever want to read in a math class is you're doing something by trial and error. There's a whole technique of factoring by trial and error. It's fast once you get used to it. You also don't want to read something that says will require some ingenuity and ad hoc method. An ad hoc method is a method that you invented to solve exactly one problem. So that's not a nice piece of advice to give, but our author is being honest. Some of these integrals are actually really quite hard, and it does require ingenuity. There's no specific strategy for every one of these, but there is a good way to start this one. Anyone happen to see it? Exactly, absolutely. I don't know the direct integral of this thing, but we know if you can find an integral antiderivative of secant squared and -1. So that's the thing to use on this one. So it starts off immediately. Let's write the identity to the right before we use it by saying tangent squared of x, if you're looking at this identity, just subtract 1, is secant squared of x minus 1. So we'll just plug that in. And it makes a problem where me personally, I could stare at this for about a half an hour before I realized I'm missing something. But if you see the thing, it was just this. If this happens to you on your homework, don't hesitate to just reach out and say, hey, Mike, I don't even know how to start this one. Could you help out? I'm very happy to respond to those kinds of emails. I say this a lot. Not a lot of people takes me up on that. So just to reiterate, you are welcome to send questions by email. Office hours is obviously better, but it's hard to always get in contact, especially if you're a remote student or coming in from a further campus. So here's the next step. It's a definite integral from pi over 4 to pi over 3 of this thing, secant squared x minus 1 dx. This time we don't use a arbitrary constant of integration c because we're going to use the fundamental theorem of calculus. First thing, antiderivative of secant squared. That one's just a tangent x. Minus antiderivative of -1 is just an x. We'll evaluate this whole thing from pi over 4 up to a pi over 3, which means at this stage, the calculus is essentially done. Once we write down the next expression here, what we're really doing now is reviewing trigonometry. So let's work this out on the right. Usually thing in orange means things you don't have to put down on your assignment for credit. Sometimes it's an extra comment or review material like we're looking at here. We have two pertinent angles we need to deal with. The nice one's pi over 4. Pi over 4 is nice because tangent at pi over 4 involves in the numerator sine pi over 4. That's this quantity. Anyone recall what it is? The hint is it's exactly the same as the cosine one, if I can draw that arrow convincingly. Trig is always one of those things where it's easy to kind of brush up on it, but if you haven't used it for like, for me personally, an entire summer, it's easy to also leave your head. It's one of those things that's perishable. But one of the things I do print on exams is this right here. You can count on this on exams 1 through 3 and the final exam. And this is just my way of helping out if you feel like you're not sure what a trig evaluation should come out as. So let's paste this down here as further support. So if we're feeling a little foggy, this is provided on a real exam, and it indicates both cosine and sine have the values √2/2. But that's nice. That means this whole thing is just a clever way to write the number 1. So lower limit of integration, no big deal. That's just 1. We need to do it again for pi/3, so that's going to be our next one. Let's see here. We'll leave the table there. Let's draw pi/3 on the diagram. It's about like that. Now there's one value that's easy to pick here. If you had to guess a number, it's a number between 0 and 1. To me, looks like a half, even though it's not a perfectly drawn circle. Then this one is the value you would see on a trig table that's close to 1. That's the √3/2. So that's what happens with the pi/3, a half for cosine, √3/2 for sine. Putting that all together, let's see here. I'm going to go to the new page on this. Tangent pi/3. Kind of annoying to calculate, but the sine value goes up in the numerator, √3/2. Cosine value goes into the denominator, 1/2. And then you're on your way. Whole thing reduces to just √3. All this is just a reminder that if this was a problem on, say, exam 1, the final exam, if you got to this step, tangent pi/3 minus pi/3, and didn't evaluate that, you might lose that point. No big deal, but it's a reminder we need to evaluate our trig functions. So that's the upper limit of integration. Now for the lower one, don't forget the minus, and we do need a parentheses. Tangent pi/4 minus pi/4. So finally, this turns into, that is a √3, looking it up on the right, minus pi/3. The negative is going to distribute inside, so this turns into a -1. And this will turn into a positive pi/4. Well, we got it, folks. That's what the answer should come out as. Yeah, go ahead.
Didn't you say on like, one of the last examples, like last week or whatever, that since it's on a definite integral, the negative doesn't distribute in?
Well, a negative right here would distribute in if it's going through the group, but let me think about that. It would have been here. We should be able to find this one. Probably towards the end of the notes is what I'm guessing. Let me see if I can find it. There was some weird issues with trickiness on this negative sign, but I don't think that was necessarily the example you're thinking of.
I don't remember.
Let's see here.
Not actually, X5, X, right there, that.
Oh, this one right here.
Yeah.
So we had,
Is that it?
sorry, say again? Well, we did put a negative right here on this one, but we're looking for issues with parentheses and distribution. Yeah, I'm not quite finding that particular one, but
I think there's some.
yeah, let me know if you stumble on that problem again. But with this one right here, because we're going from pi/3 to pi/4, well, rather the bigger issue was because this has 2 terms, we always have to include a negative sign right here from upper limit to lower limit. That's what we're seeing on those old notes. But because there's 2 terms here, that negative sign would distribute on the very next step for this one specific situation. There might have been some other technical issue we were looking at in a different problem, maybe double negative stuff like that. But in this configuration, it would have to distribute through. But let me know if you spot that problem again. I'll be very happy to take a look at it.
Alright.
Other questions or comments so far, folks? Okay, still more you could do to it, but let's imagine you're on your real exam. You probably don't want to add these fractions together. But I'd say this is a pretty good stopping point. If you decide to go further, you probably see an answer like this in the back of the book. Root 3 minus 1. Let's see, pi over 3, that's going to be 4 pi over 12, 3 pi over 12. So this is plus pi over 12. That's nice to do, but honestly, I'm okay with this stuff too. This is where the calculus ends. Only take it a little bit further if you're trying to line up answers with the back of the book, try to get it in the same form. So the reminder on this one is sometimes there's nothing special going on except some random identity you need. And that was the reminder here on this problem. 7 and 37 start off that way as well. You need a trig identity to begin. If you're not sure where it is, don't hesitate to reach out. I'll be happy to help. Let's see, we've got 7 minutes and some change. And we have one more integral to get through. You know, this is a kind of fun one. I don't think we want to rush through C or D, 2 more to get through. So I'd say this is probably a pretty good stopping point for us. Any questions at all then, folks, before we call it a night?
If I'm doing this, what would you say that course materials link to the work is? What could be?
Sorry, say again. Yeah, this one right here. Another student was saying it's for online materials. Say if we were using WebAssign or MathXL or something like that. I think that's what that was supposed to be for. I'm gonna try to get some better clarification from the administration. They've been quiet. I think they're just scrambling, I guess, is what they're doing. I might end up just removing this from the class because we don't use online materials. We're just doing homework directly and traditionally. Any other questions at the moment? Okay, well, if you do have more, don't hesitate to hang out. I usually get going here about 8:30, but I'm happy to take questions after. Otherwise, see you all folks on Wednesday's class. We'll pick up here on part C.
Is the book bundle, they actually give you the books? I thought they were just renting them to you.
I think they're giving, it's just a rent? Oh, geez, I should put that down.
It's for all.
So is it correct to say the book bundle is exclusively for renting books then?
I think so.
Oh, they never talk about that. People actually want books, especially in math, engineering and such. It's another issue to raise.
Yeah, it didn't really clarify in the emails too.
Yeah. They sent us a bunch of spam emails basically with, look like marketing materials practically, not actual practical advice on how to navigate this. Yeah. Yeah, sorry about that. I'm not a fan of how this is going. Hopefully they make this a little bit better. I'm not a fan of the mandatory opt-in either. That just doesn't even seem ethical in the first place. So if anything you could do to push upwards, you could talk to your department chairs, you could talk to the provost of the university. They need to know that kind of stuff about how this is going because I don't think it's our finest hour, to be honest. Well, have a great night, folks. See you all in Wednesday's class. Thank you. Have a good one, folks, in Zoom as well.
Did you see the, start grading, you start grading the assignments, like, this Thursday or whatever?
Yeah, I usually grade them once a due date goes by. So my first one, I'm gonna grade on Thursday. And because I think you turned yours in digitally, right?
Yeah.
If you decide you need to make a modification to that, that's completely fine as well.
On that one,
Mhm.
there was one that I wrote on there, like asking if it was equal to what the book said the answer was.
Oh, gotcha. I didn't quite see that when I downloaded your homework, but
Yeah.
yeah, I'm happy to come back to that if you have a question on it.
Okay.
You could like take a screenshot, and just send it to my email, and I would be happy to take a look at it with you.
Alright, I'm gonna do it.
Awesome. Yeah, if you decided you want to make a correction on anything, that's no trouble either. It's not like I'm gonna redo any grading or anything like that. Thanks, you too.